Welcome to another honors physics video. This is on rotation as it applies to Newton's second law. Just to remind you, Newton's second law is summarized as net force equals ma in magnitude. The rotational equivalent of that is torque, which instead of m we have moment of inertia, and instead of a we have angular acceleration. Let's begin by taking a look at a pulley. The pulley has radius r and mass mp. If we were to attach a bucket to that of mass mb, the bucket would supply a force because of its weight, which would be countered by the tension in the string. That tension would supply a force on the pulley. The bucket would accelerate downward, while the tension on the pulley would produce a torque, causing an angular acceleration. Let's explore the torque on the pulley. So if I look at the accelerating pulley, Newton's second law describes this action as net torque equals I alpha, where I is the moment of inertia of the pulley and alpha is its angular acceleration. Torque, if you recall, is the product of r times t, and these have to be perpendicular, which they are. So substituting in, we get the lever arm, or the radius here, of r times the tension is equal to I alpha. The moment of inertia for the pulley, if we look it up, is 1/2 mass of the pulley times r squared. If you have not watched this separate video on moment of inertia, now would be a good time to pause, go to the Honors Physics playlist, and take a look at that video. Separating the r's and then combining the r times alpha, we can again make that substitution for acceleration. Noticing that I have the radius on both sides of the equation, I can reduce that, leaving me with my expression for tension as 1/2 mass of the pulley times the linear acceleration. Let's look at the whole system again. Now, if we were to focus just on the bucket undergoes translational motion and is defined by Newton's second law in this form. Looking at the forces, we have the weight in the direction of the acceleration and the tension opposite. Substituting the weight in the direction of the acceleration minus the tension for the net force equals the mass of the bucket times its linear acceleration. Reviewing the tension from the pulley, we can then look to substitute that into our equation for tension. Collecting our terms with acceleration on one side of the equation, and then factoring out the acceleration, dividing by the masses, leaves us with an expression for the linear acceleration of the system. That acceleration is, as Newton had stated, with the unbalanced force, which is just the weight of the bucket, divided by the total inertial characteristics of the system, which includes the mass of the bucket plus the portion of the pulley that provides resistance.